This question asks you to determine which statements correctly describe how the length_scale_bounds parameter, which sets limits on the length scale of an RBF kernel in Gaussian process regression, affects the model. I'm testing your understanding of how the bounds influence the optimization process and the final model's characteristics. Let's tackle each statement individually. I think this statement is false. While the optimizer tries to find the best length scale within those bounds, it's not guaranteed to land perfectly within them. The final length scale might be very close, but it's not a hard and fast rule that it has to be exactly within that range. I believe this statement is true. Setting wide bounds, like 1e5 to 1e5 here, allows the algorithm to explore a broad spectrum of length scales. This can help avoid overfitting, when your model is too complex and fits the training data too closely, or underfitting, when the model is too simple and doesn't capture the patterns in the data. It really helps strike that balance. This is true as well. The bounds act as guardrails, limiting the length scale values the optimizer can explore during training. This directly affects the smoothness of the resulting Gaussian process model. A smaller length scale implies more wiggly behavior, whereas a larger length scale indicates smoother curves. I find this statement false. Even if you're not using gradient-based methods, like Bayesian optimization for instance, these bounds still help. They're beneficial because they constrain the search space, making the optimization process more efficient for pretty much any optimization method, not just gradient-based ones. I'm focusing on Gaussian process regression, a powerful machine learning technique that uses probability distributions to predict values. It's like having a smart guesser that tells you not only its best guess but also how confident it is in that guess. I'll be explaining how we fine-tune this guesser to get even better predictions. In our Gaussian process regression, the RBF kernel's length scale parameter controls the smoothness of the predictions. Imagine drawing a curve to fit some data points. A small length scale makes the curve wiggle a lot, fitting the points very closely, like a super detailed map. Conversely, a large length scale creates a smoother curve that ignores minor variations, like a very general overview map. We want to find just the right amount of detail. To find the ideal length scale, we need to search for it. This parameter sets the limits for that search. I think of it like setting boundaries on a treasure hunt. I tell the algorithm to look for the best length scale only within a specified range. This prevents it from wasting time searching impossible or unrealistic values. These bounds directly influence how smooth or wiggly the final prediction curve is, helping us control model complexity. This is the core question of the quiz. We are investigating the impact of setting boundaries on a parameter that controls the smoothness and the prediction quality of a statistical model. The question here is about understanding how the range that the algorithm searches affects the quality of the model. I'm using Gaussian process regression, GPR, with a radial basis function, RBF, kernel. This means my model uses probability to make predictions, and the RBF kernel influences how smooth these predictions are. Understanding how to set boundaries on the parameters is essential for building a reliable model. This refers to the process of finding the best settings for the model's parameters, like the length scale, to improve its prediction accuracy. The process of finding the optimal settings is called hyperparameter optimization. By setting wide bounds, I allow the algorithm to explore a wide range of smoothness levels. This avoids overfitting, a model too closely tied to the training data and poor at generalizing, or underfitting, a model too simplistic and failing to capture underlying patterns. These bounds directly limit the possible values the length scale can take, which directly impacts the prediction curve's smoothness. The range sets the limits of the curve's smoothness. This is incorrect. Even without gradient-based methods, setting bounds is beneficial. It helps narrow the search space for any optimization method, making the process more efficient. It's like giving a helpful hint to any treasure hunter. The algorithm tries to find the best length scale within those boundaries but doesn't guarantee it will end up exactly within them. It's like aiming for a target. You might get very close, but you might not hit the bullseye exactly. I see this row refers to the space where the optimizer searches for the best length_scale. It's like searching for a treasure. The lengthscalebounds define the boundaries of the treasure map. The optimizer won't look outside these boundaries. This line specifically sets those boundaries. Is scientific notation for 0.00001, and 1e5 is 100,000. So, the optimizer will only consider values for the length underscore scale between 0.00001 and 100,000. It's a pretty wide search space. This line explains what LENGTHSCALEBOUNDS actually does. It's simply stating that LENGTHSCALEBOUNDS sets the limits of the area where the algorithm looks for the best LENGTHSCALE. Think of it like this: we're looking for the best length scale. This line tells us the range where we'll look for it. This question asks you to determine which statements accurately describe the role of length underscore scale underscore bounds in a Gaussian process regression model using a radial basis function, RBF, kernel in Sklearn. I'm assessing your understanding of how this parameter influences the optimization process and the final model's behavior. Let's dive in. I agree that this statement is true. By setting a wide range for the length scale, 1e5 to 1e5 in this case, representing 0.00001 to 10000, the optimizer has a large search space. This prevents the model from becoming too complex, overfitting, or too simplistic, underfitting, by allowing it to find the optimal length scale. A wider search space enhances the likelihood of identifying the optimal length scale that effectively balances model complexity and generalization. Absolutely true. The length underscore scale underscore bounds directly limit the range of values considered during the optimization. Remember, a smaller length scale creates a more complex, wiggly function, while a larger one leads to a smoother function. So, constraining the length scale directly impacts the smoothness of the resulting Gaussian process. I'm setting the boundaries to guide the search for the optimal level of smoothness. This is false. Although the optimizer tries to find the optimal length scale within these bounds, it's not guaranteed to converge to a value strictly within the specified range. The final value might be very close to the boundary. The bounds act as guidelines for the search, not as absolute limits on the final result. Incorrect. While gradient-based methods benefit most, the bounds help all optimization methods, not just those using gradients. Any optimization strategy benefits from a more focused search space, leading to greater efficiency. So, I consider this statement inaccurate. This question asks you to assess your understanding of the LENGTHSCALEBOUNDS parameter in Sklearn's Gaussian process regression using an RBF kernel. We'll examine each statement to determine its validity. I found this statement to be false. While the optimizer tries to find the best LENGTHSCALE within the specified bounds, it's not guaranteed to land precisely within them. The final LENGTHSCALE might be very close to a bound, but it won't always be strictly within the range. This is true. By setting wide bounds, I allow the optimization algorithm to explore a vast space of possible LENGTHSCALE values. This helps avoid both overfitting, a too complex model, indicated by a small LENGTHSCALE, and underfitting, a too simple model indicated by a large LENGTHSCALE. I also find this statement true. These bounds act as a constraint. They directly limit the range of LENGTHSCALE values considered during optimization. Since the LENGTHSCALE directly controls the smoothness of the Gaussian process, restricting its range inevitably influences the model's final smoothness. This is incorrect. Even though gradient-based methods benefit most from well-defined bounds, all optimization methods, including those that aren't gradient-based, like Bayesian optimization, use bounds to limit the search space and become more efficient. It's about smarter searching, not just gradient calculations. This refers to the process of finding the best settings, hyperparameters, for a machine learning model like our Gaussian process regression model here. In this specific case, we're tuning the LENGTHSCALE hyperparameter of the RBF kernel. The goal is to find the LENGTHSCALE that yields the best model performance. I'm using GPR, a powerful machine learning technique, with a radial basis function, RBF kernel. The RBF kernel is a common choice because it's flexible and mathematically convenient. This setup is perfect for modeling smooth, continuous relationships in data. This parameter within the RBF kernel controls how far the influence of one data point extends to its neighbors. A small length scale means only nearby points matter, leading to a more wiggly function. A large length scale signifies that points far apart influence each other, resulting in a smoother function. Think of it like the reach of each data point's influence. This tells the optimizer the allowed range for length_scale. It's like setting boundaries for a search. We don't want the optimizer to explore values that are unrealistically small or large, which could lead to poor performance. I set the bounds, 1E5, 1E5, to give the optimizer a broad search area. This is usually a good starting point to avoid overfitting or underfitting, allowing the model to find the just right level of smoothness. This question assesses your understanding of how lengthscalebounds affect the optimization process in GPR with RBF kernels. We'll analyze each statement to determine its validity. The radial basis function, RBF, kernel is a crucial component of the Gaussian process regression model. It defines the relationships between data points, essentially determining how similar or dissimilar they are based on their distance in the feature space. Choosing a different kernel would change how the model learns from the data. This is a hyperparameter of the RBF kernel that I tune to control the smoothness of my predictions. It dictates the reach of influence of each data point. A larger value leads to smoother predictions, while a smaller value results in more wiggly predictions. Finding the right length scale is essential for achieving good model performance. This question asks you to understand how the length_scale_bounds parameter in scikit-learn's Gaussian process regression, GPR, with a radial basis function, RBF, kernel affects the model. Let's break it down. We'll look at each statement and see whether it's true or false. Get ready. I agree. The length_scale_bounds directly control the range of values that the optimizer can use for the length_scale parameter. This parameter determines how smooth the resulting Gaussian process is. A smaller length_scale gives a more wiggly, complex curve. A larger one produces a smoother curve. By setting bounds, you are directly affecting the smoothness and flexibility of your final model. Yes. That's correct. By setting a wide range, like 1E5, that's 10 to the power of -5 to 10 to the power of 5, the optimizer has a lot of freedom. This helps avoid overfitting, a model too closely tied to the training data, not generalizing well, or underfitting, a model that's too simplistic and doesn't capture the data's complexity. I'd say this is false. While gradient-based methods benefit greatly, the bounds help all optimization methods. They focus the search, making the optimization process more efficient, no matter the technique used. This statement is false. The optimizer tries to find the best value within the bounds but might end up very close to a boundary, but not necessarily exactly inside it. Think of it like aiming for a target. You try your best, but you might not hit the bullseye perfectly.